Okay, Assalamualaikum and good afternoon, everyone. So welcome back from the holidays. So today we will have two more presenters for today's session. So we will have Jian for the first one, and Hon Xiao Tong for the second one. So I think let's proceed with the first presenter of, from Jian. Sorry with pronunciation. And then he will be talking about substitution effect of methylammonium organic cation in lead-free bismuth-based perovskite via microwave-assisted solvothermal method for photovoltaic application. So please, Mr. Lau.
Okay, thanks, Rob. Okay, so
do speak louder in the mic, please.
Oh, okay. What about the volume now?
Slightly better.
Okay, now I will keep keeping this volume lah. So am I good to go, Prof?
Sure. Go ahead.
Okay. Good day to Associate Prof. Dr. Hishamuddin, Chairman for this session, every audience, and also every audience in this section. And my name is Hon Jian, and I'm a student from Ion 2 under supervision of Dr. Josephine. Today, I'm going to give a presentation about my research progress of my PhD project with the title of Substitution and Doping Effect. It's Substitution Effect of the Methylammonium organic cation in lead-free bismuth-based perovskite via the microwave-assisted solvothermal method for photovoltaic application. And this presentation is divided into 12 parts. And in 2019, a first metal halide perovskite, which is a methylammonium lead bromide, had demonstrated promising optical properties for photovoltaic application. And this perovskite structure is exhibiting a ABS3 structure where all the ions in this structure have a different functions and it can be engineered by different element combination. Since then, researchers have been focusing their efforts on metal halide perovskite, and with a notable advancement in lead-based perovskite halides. And however, the lead-based perovskite is still suffering from its two major issues viral to the application, notably toxicity and toxicity of the lead and the poor stability under the ambient condition. Thus, effective strategies are desired to address the toxicity issue of the lead-based perovskite halides. And there are three main perovskite halides are proposed as a lead-based perovskite replacement material. It's given a tin and copper is introduced due to their isovalent properties to the lead, Pb2+, and unfortunately, both of their perovskite structure easily decompose or oxidize under ambient condition, making them unsuitable for the lead replacement. Hence, Bismuth 3+ is recognized as an alternative replacement for lead, and due to its similar electronegativity, and also the ionic radius and electronic configuration to the Pb2+. And relative to the bismuth-based perovskite halides, there are three main types of the structure discovered so far, and each of them assert their own pros and cons. In general, all of the structure is benefits from the promising stability, but each of them suffer from the disadvantages of a large band gap, deep defect, and non-ideal band gap for the 329 structure, difficulty in material synthesis, and non-ideal band gap for 2116 structure, and the is a plus 3B structure is limited to the iodide base and also difficult to be synthesized. And there are a variety of research have been done on the bismuth-based perovskite materials engineering, which included the doping or alloying through the organic A cation, inorganic A cation, B cation, and X anion. And due to the consideration in the production cost, material scientists are more likely to engineer the perovskite material through the A cation rather than the B and X anion. And among all of the A and X ion for the bismuth-based perovskite, the cesium and the bromide stand out the most due to the stability in the bismuth-based perovskite, making them the most studied structure in the bismuth-based perovskite material. And in general, they are two thermodynamically stable bismuth-based perovskite structure, which is a single perovskite of the CS3Br2Br9. And from now on, I will pronounce it as a 329 structure, and the double perovskite CS2AgBiBr6 and 2116 structure. And each of them exhibit their own pros and cons, having a desired direct band gap while it having a ultra-fast carrier lifetime features. And 2116 structure have an ultra-long carrier lifetime, but it suffers from the indirect band gap. And there are two undesired features in a 329 structure and 2116, and which deteriorate their performance in the photovoltaic application. And in order to overcome these undesired features in the materials, organic cation methylammonium Ma+ is favorable for the enhancement in the carrier lifetime and the band structure engineering. Also, as best of my knowledge, no research was done on the Ma substitution effect in the CSBIBR-based perovskite structure up to date. Hence, the effect of the Ma cation substitution in the CSBIBR-based perovskite materials are worth to explore in order to achieve a better photovoltaic performance close to a Schottky Quasar limit. Okay. So beside from the material properties perspective, sample preparation is also a bottleneck for the production of a high quality material. And the material synthesis method for the Bi-based or the bismuth-based perovskite nanocrystal is over dependent on the RP and the HI method, which is the reprecipitation method and also the hot injection method. And both of them have their own pros and cons. Thus, an alternative method must be developed to produce the perovskite material without compromising the advantages of the RP and the HI method. And this can be achieved via the microwave-assisted Solvothermal method. Okay, and hence, based on the previous statement I stated before, the objective for my PhD project are to synthesize the lead-free CSBIBR-based perovskite via the novel microwave-assisted Solvothermal method. And the second one is to investigate the substitution effect of the methylammonium bromide, organic cation on the structural and optical properties of the CSBIBR-based perovskite. And the third one is to investigate the effect of the Ma+ organic cation substitution on the photovoltaic application performance of the BIBR-based perovskite. And to predict the material structure and properties, Material Studio is used for the material simulation based on the first principle calculation, DFT. And from here, we are able to generate the band structure, density of state, and the structural properties of the CSBIBR-based perovskite material after substitute before we substitute with the Ma organic cation. And in the typical synthesis of a CSBIBR-based perovskite composite synthesis, all the reagent was mixed together and placed in the glass vial, and the mixture solution was then undergo the microwave-assisted Solvothermal method synthesis in a scientific microwave reactor at 160 degrees Celsius for 2 minutes. And after the reaction was complete, the supernatant was obtained and washed with the absolute ethanol and undergo centrifugation process to obtain the sample. And all the reagent used to prepare the CSBIBR-based material was tabulated in this table. And in this project, the synthesized sample will be characterized through the XRD, Raman, UV-Vis, PL, TED, BL, TRPL, PSAM, EDX, and solar simulation in order to achieve the objective stated before. And for the solar cell fabrication, the ETL and the HDL, which is the electron transport layer and hole transport layer, will be spin coated on the conducting FDO glasses, and the sample will be sandwiched between them, and an electrolyte is applied to the sample. And now let's move on to the result for the first projective of this project. And in the optimization of microwave-assisted Solvothermal method in this study, solvent plays a vital role as it decides the reaction atmosphere. And octadecent, a solvent that is commonly used in the hot injection method, is first tested, and the materials prepared in the ODE induced the undesired phases, which included oxide precursor, unreacted precursor, and the secondary phase. And the bismuth oxide formation is caused by the atmospheric condition throughout the reaction process, as the reduced bismuth 3+ ion react with the oxygen prior to the undesired phases formation. As a result, the CS to the PBIBR and to the AGBR precursor ratio in the reactant solution is altered and by the bismuth bromide oxide formation, and tends to form a more stable secondary 329 structure perovskite and with some leftover impurities. Then, without a huge modification, IPA is introduced with this system and successfully synthesized the desired phases with high purity. And this compatibility of the IPA solvent in the microwave-assisted solvothermal method can be explained by the boiling point of the solvent selection, which is the crucial part to create the high pressure in the reaction environment. And the boiling point of IPA is around 82.5 degrees Celsius, which is much lower compared to the oxidation or DE, which is in 317 degrees Celsius. Thus, the IPA will evaporate under the fixed reaction temperature and create an IPA concentrated atmosphere that prevent the bismuth oxidation. And ligand selection is also found to be crucial for the bismuth-based perovskite as well as in the microwave-assisted solvothermal method. In this study, OLA and OA, which is the oleic amine and also the oleic acid, are introduced as the ligand for the perovskite formation. OLA is known as a good coordinating agent in controlling the crystallite size of the perovskite during the crystal growth stage, and a reductant in improving the Bi precursor solubility. However, the OLA must be protonated first before the ligand nanoparticles formation, and the protonation process can be completed with the aid of the oleic acid. And at first, the oleic acid will be deprotonated, and first by forming a carboxylate ion with an extra proton. Then the additional proton will protonate the ammonium group in the OLA and ready up the OLA for the nanoparticle surface specification effect through the OLA-BR attachment. And also, the deprotonated OA will help to separate the unreacted precursor by forming the oleic products that can be removed by the washing process. And nevertheless, the purity and the physical properties of the products synthesized are decided by the OA to OLA ratio, and excess of the OLA in the system will lead to the undesired impurities or secondary phase formation, and as supported by the previous perovskite study regardless of the synthesis method. And hence, the OA to OLA ratio is optimized at the 2:1 in the microwave-assisted solvothermal method for the synthesis of the CSBIBR-based double perovskite. Not only the double perovskite, single perovskite as well, after the justification through the XRD measurement. So after the solvent and ligand optimization in the microwave-assisted solvothermal method, AGBR precursor is detected remain in the IPA for the double perovskite synthesis, which is a 2116 structure, and accepted as an impurities. And with 2 ml of the hydrobromic acid added into the reaction system, the incomplete ionization of the silver bromide issue can be overcome. And aside from the assisting in the complete dissolution of the silver bromide, the acidity of the hydrogen bromide HBr also promotes the OLA protonation while providing excess Br anion for the structure growth. However, excess of the HBr will increase the polarity of the reaction system and result in the perovskite dissolution. And the usage of the concentrated acid is also not recommended in the microwave instrument, which may reduce the instrument lifespan by acid corrosion. Hence, in this study, we only optimize the HBr amount in 2 ml without compromising the material's purity. So the experimental XRD pattern for the 2116 structure shows an good agreement with the simulated XRD, suggesting that the structure has been successfully formed. From here, we can see that the 2116 structure exhibiting a cubic crystal system with a space group of FM3M. And in this structure, silver bromide and the bismuth bromide octahedral are arranged alternately throughout the entire structure and are separated with the cesium 8 ion. And the same condition also displayed for the 329 structure, which the experimental profile match the simulated profile. And the 329 structure shows a trigonal crystal system with a space group of P3M1, which the BIBR octahedral layers with the void between the layers filled with the CS cap. Sorry. Okay. For an organic Ma329 structure, same structure system, same crystal system and the space group was found on this structure as well, compared to the CS329 structure. And all of the peak match with the simulated XRD pattern, but with a different peak intensity ratio. And this will be explained and discussed further on. And for next is all of the XRD quantitative results was tabulated in this table, and the quantitative result shows that the experimental, simulated, and the database obtained profile shows a similar value in the lattice parameter, volume bond angle, bond length, and this indicates that the BIBR perovskite structure had been successfully formed through the optimized microwave-assisted solvothermal method. And the PCM structure for the 2116 structure shows a nano-cubic sized particle ranging around 100 nanometer, revealing the nature of the 2116 structure cubic system. And the chemical composition of the 2116 indicates a bromide-rich condition or the cesium deficient condition occur in this particle, as this condition is resulted from the bismuth-rich reaction medium that necessary for the silver bromide precursor solvation. And for the 329 structure, the PCM image show a hexagonal structure arising from the crystal system nature, and the near ideal stoichiometry is found in this structure. And for the Ma329 structure, it also shows a large particle size distribution as shown in this PCM image. And the chemical composition also shows that the Ma329 structure having a near ideal stoichiometry. And for the Raman, to further verify the purity of the materials form, Raman spectroscopy is also used to obtain the vibration spectra of the structure. And all of the structure is matched with their respective vibration mode, shows that the microwave-assisted solvothermal method is able to synthesize a high quality and pure phase of the bismuth-based perovskite. And for next is a TDPL. This one is time-dependent, temperature-dependent photoluminescence spectroscopy. And the TDPL of the all sample was shown in this slide. And the 2116 structure only exhibit a PL peak with a broad FYPHM located at 2.0 eV, while the 329 structure for MA and CS show two peaks at around 2.5 and 2.7 eV. And to obtain the TDPL data, in order to extract maximum information from the TDPL, the data obtained is then replot and fitted into three different equations, which is the Vashni, Arrhenius, and boson equation. And in general, 2116 structure exhibit a high localization degree and thermal activation energy and phonon contribution. However, the phonon in this structure can be suppressed when the temperature is below 200 Kelvin. And for the CS and the Ma329 structure, all of the peak shows a low degree of localization effect, but the peak 2 of the CS329 structure located at the 2.7 eV and the peak 1 for the Ma329 structure located at the 2.5 eV shows a high thermal activation energy. Also, a high acoustic phonon contribution was found on the peak 2 for the MA, which located at 2.7 eV. And this fitted graph on the TDPL parameters is useful to provide an insight to the material optical properties. And also, the UVB spectrum for the 2116 structure shows a longer absorption tail compared to the 329 structure. And this could attribute from the indirect bandgap nature of the material, while the peak located at around 410 nanometers is attributed from the direct transition in the structure. And the case is different for the 329 structure. The first peak is located at 480 nanometers, which is attributed from the exciton band transition, while the second peak at around 410 nanometers is originated from the direct band structure, direct band transition as explained in the Iliad model. And the absorption spectra obtained of all of the sample was then replot with the tau equation, which allowed the detailed investigation in the material electronic transition. And the band structure, DOS, PDOS, was generated from the DFT calculation for the energy band gap justification of the material. And all of the bismuth-based structure shows that the lower band gap value is only originated from the octahedron in this structure. While the AK ion is not contributing much in the band structure engineering, as it only an inclusion in the perovskite structure without having any physical bonding to the octahedron. And all of the bismuth-based perovskite shows the low band gap value. Hence, from the simulated band structures and determine optical band gap, the direct transition is near to each other, but the indirect transition is deviate significantly. And this discrepancy is resulted from the limitation in the GGA function, which is a generalized gradient approximation function that used in the energy band gap calculation and can be countermeasured by using a hybrid equation, the HSE equation, with a spin orbit coupling consideration. And also the PL peak indicates that this material is suggesting an indirect transition as the value is close to each other. But in reality, it's not, because the band-to-band transition is not occurring and is originated from the color center, and the detail will be presented on the next slide. And for the CS and MA329 structure, the simulated and experimental realized value is an agreement showing that both of the materials showing a direct transition. And now the carrier generation and recombination for the 2116 structure will be illustrated in this animation. The red dot represents the electron in the valence band maximum, BBM. And for the direct allowed transition at the G symmetry point, the exciton at the VBM will be excited to the conduction band minimum, CBM, and generate an exciton. And after that, the exciton will undergo a recombination at the same symmetry point along the electron recombination pathway. And there's a color center with the value around 2 eV, with a FWHM of around 0.3 eV or 300 MeV. And the exciton will be trapped before it recombine back. And the trapped exciton will further recombine with the holes in the BBM and release or emit the energy equivalent to the color center energy band gap. And for the indirect allowed transition, an exciton same will be generated at the point G. Then the exciton will experience an exciton scattering process in order to lower down the exciton binding energy and the effective mass. Once the exciton arrives at the CBM at L point, the exciton will recombine back with the holes in the BBM at point X. Hence, this material will be much more preferred and color center emission instead of the band-to-band transition, as indicated in PL study, which showing that an emission energy of around 2.05 eV. And I think I will stop at here because there's insufficient time. I will straight away skip to my conclusion. Okay. So in conclusion, I will just conclude for my first objective. So the lead-free bismuth-based perovskite and its composite have been successfully synthesized through the microwave-assisted solvothermal method. And this development for this novel material with an optimized parameter will provide a good insight or open up a new path for the bismuth-based perovskite materials development. So before so these are some future planning, because I only left around 10% of my project, haven't received the result yet. So these are my Gantt charts during my PhD study, and these are my list of publication. And before I end my presentation, I would like to acknowledge the financial support from the FRGS, and also special thanks to Dr. Nana, Dr. Farah, Dr. Tan, Dr. Huda, Dr. Kok from agency, and also the Amel, which is helping me in generating or calculating the band structure calculation. So these are my references used in this slides. And thanks for your attention.
Okay, thank you, Mr. Lau. So now let's welcome some Q&A from your peers. Anyone?
Hello, Doctor. Good afternoon.
All right, go ahead.
Okay. Mr. Low, congratulations with this your wonderful presentation. It is really a wonderful one. So in your presentation, it seems like you have synthesized a very new compound. That's what led to the simulation, so that you can confirm whether the new compound synthesized is formed or not. And I have seen that you were able to confirm the formation through the characterization like XRD. So I don't know whether you have taken the tolerance factor into consideration, which is another factor for confirming whether the new compound or new perovskite is formed or not, because there is a set of value of tolerance factor that a new compound must be within that range before it is considered to be a perovskite structure. So I don't know whether you have that consideration. This is my first question. Then second one, I know that based on my little knowledge, that when you are going to substitute an element into a new compound or into a already formed compound, the radius of the elements, the two radius are going to be considered. That there is a certain limit that those two radius must not pass. Like I could remember in some previous studies that they mentioned the difference between the two radius must not exceed 15%. So I don't know whether you have put all those into consideration. Thank you. These are my question and maybe suggestion. Thank you.
Okay. Thanks, Bashir, for the good questions. So the question is basically about, the first question is about the tolerance factor. And the second question is about the tolerance, right? The how many percent it must be smaller or bigger compared to the original cation radius or ionic radius. So I will show my work before for my FYP. So for this, I have done for the tolerance factor, and I have calculated for, before I done the substitution, I have to look for the potential candidates or potential cation to be substituted into the 329 or 2116 structure, or in other words, it's a Bismuth perovskite structures. So there's a lot of consideration I have to taken before I proceed. And I have calculated using a worksheet. I'm not sure, I forgot already I put at where, but definitely I have calculated it. But basically I calculate with the Goldsmith tolerance factor. So let me zoom in. So this current Goldsmith tolerance factor is a well-known perovskite equation that used to predict whether the structure will be formed or not. But this equation is limited in the oxide, and it's very inaccurate for the halide perovskite prediction. So that's why I moved to the MGTF, which they have modified some of the equation with some effective radius. And further on is the new tolerance factor. If you included the organic, it will become a different things. And with these factors, they have successfully boost up the accuracy for the equation to be predict whether it's formed the perovskite structure or not. It has successfully boost up the accuracy up to 80%. So this is my FYP works previous time. But yeah, of course, I have done on my project as well. Definitely, it's fall in the formable perovskite structure, but with a different crystal system lah, which we have to take consideration after that. And also the octahedral, I have, other than the tolerance factor, I also consider the octahedral factor. And this octahedral factor is very crucial in the perovskite structure, since that normally in the perovskite halides, especially the bismuth-based perovskite, it will form an octahedral. As you seen at here, this is the octahedral. is a small cube inside the lattice or lattice structure. So this is an octahedral, and this octahedral, the factor of the octahedral, it will, as you can see, what is the value if you substitute the radius of the B and X into this equation, and the answer or the value it calculated, it will give you some hints whether the structure is stable or not before we forming the perovskite structure. But because in perovskite structure, it must be the octahedral factor must be fall within this region. Okay, so Bashir, am I answering your question?
Yes. Yeah. Right.
Okay, thanks for your question.
Okay, I think that's if there's any other question, one or two from your peers or even from your co-supervisor who's here. No questions?
Hi, Prof. This is Chan Ka-Fai.
Okay.
Yeah, off the team first. I have one question for Lo. Just want to know what is your expectation for the TGA? You are talking about thermal stability. What do you mean by thermal stability?
Okay, the thermal stability, because I'll go back to my topic first, because I'm doing the substitution effects of this organic cation and replacing the inorganic inside the 2116 structure. So it means that the Ma will be substitute the Cs, and all of the others are the inorganic. So once I substitute, because it's the inorganic element or compound, so we know that the organic is quite volatile. It depends on the compound compared to the inorganic. So in this also in this my study, I wish to apply my materials for the photovoltaic application, and we know that the photovoltaic is basically the sunlight. We convert the sunlight to the electrical energy, which we must shine our sample. Our sample is clipped or inside the devices, and it will be shine under the sun illumination. And it might be the temperature might be goes up over time. And if the thermal stability of the material is not sufficient high, and it might be degrade after we illuminate over the times. And when it degrade, of course, the performance for the solar cell application for these materials it become inadequate. So the purpose in doing the TGA is I wish to see what is the maximum temperature it can withstand before it degrades after I substitute with the Ma substitution. And then also I expected that, of course, when we substitute some organic stuff into the structure and we take out the inorganic, of course, the organic stuff will be degraded. Yeah. So I expected that the thermal stability of my material will be decreased as the Ma substitution effect increase. Yeah. So Chan or Fai, did I answer your question?
Okay, but the thing is TGA, we cannot check the thing whether it's degrade, because TGA is what we call as is a mass decomposition stuff.
Yeah.
So
because we know what is the compound will be degraded at what temperature, because I have run for the pristine precursor, means that just like when I'm synthesizing the perovskite structure, I have a MABR, BIBR, AGBR, and CSBR, and all of these I already run the TGA, and of course from there we can know what is the point it will start degrade, and of course it was we can see we just to see the whether the original mass can withstand up to how many temperatures. That's my concern.
So it's about reusability or just mass loss?
It's just mass loss. It just mass loss. Yeah. So,
So
once
when-
one that's happened, the mass loss means that the sample definitely has something gone right. So means that it might be have some degradation. Of course, I have to recheck with the XRD lah in order to confirm my degradation.
Okay. Thank you. Good
Okay,
Alright.
answer.
thanks for the question.
Okay, I think we have used up the time for Q&A. So let's thank Mr. Lau Yin Jian for
Thanks,
the
Prof.
first presentation. So let's move to the second presenter today is Hon Xiao Tong.
Yes, Prof.
Okay, please.
So
Share
I'm sharing my presentation slide now.
Okay.
Okay, so everyone can see my slide.
Yeah, crystal
Yeah.
clear.
Okay, so may I start now, Prof?
Yeah, go ahead.
Okay, so good afternoon, Prof. Hisham, Dr. Lin, and my fellow classmates. My name is Hon Xiao Tong, and currently I'm a master's student under supervision of Dr. Lin Kempa, and my co-supervisor is Dr. Mustafa Awan Kecik. And today I'm going to share about my project with the title of Elucidating Magnetoresistive Mechanism of Nano-size NSMO Perovskite Prepared via Thermal treatment approach. So this is the outline for my presentation. I will start with the introduction, problem statement, followed by objective, literature review, methodology, result and discussion, and lastly, conclusion and reference. So now let's start off by the introduction. With chemical formula of ABS3, manganite are known as perovskite material and is shown the structure in figure below, where the green color is the A site, which is the which we will from the periodic table we will pick one of the rare earth element and one of the divalent alkali earth element to form our manganite sample. And in my study, I have chosen the neodymium and strontium to form my manganite sample. And one of the interesting properties of manganite material is their colossal magnetor resistance, where it is referring the phenomenon where the material will experience the changes of resistivity when an external magnetic field is applied. And it can be calculated by using formula below. Mr equal to delta R over R equal to RH minus R0 over R0, where the RH and R0 are the resistivity in the presence and absence of magnetic field respectively. Besides, the magnetor resistance is divided into two types, which is intrinsic magnetor resistance and also the extrinsic magnetor resistance. The intrinsic MR is predominant when there is the modification of structure by doing the topping or substitution into our sample. It will affect the bond distance and bond angle and is mainly contributed by the double exchange interaction and also the Jian distortion. While for the extrinsic MR, it is strongly related to the grand boundary effect and also the magnetic disorder layer. And the extrinsic magnetor resistance is mainly governed by the spin polarized tunneling and spin dependent scattering effect. So for my problem statement, from then till now, there are a few conventional methods that have been widely used to prepare the manganite sample, such as solid state method, Solvothermal method, and core precipitation method. However, this method do have some drawbacks and weaknesses. For example, solid state method require higher energy and temperature, and core precipitation method will produce the less favorable byproduct, which is toxic and it has the potential to harm the environment. So in this work, thermal treatment approach with lower cost, easier step, and environmental friendly operation is introduced to overcome the circumstance. And next, to control the grain size, formation, and distribution, the adjustment of parameter have been done, and most of the study are more focusing on varying the sintering temperature, sintering duration, or synthesis route to control the structure and microstructure of the sample. Meanwhile, in this study, we are trying to investigate the effect of different concentration of capping agent, which is polyvinyl pyridone in my case, to study its effect on the structural and transport properties of the sample. And in thermal treatment approach, PEP is very crucial as it acts as the capping agent to prevent the abundant growth of the nanoparticles. Besides, it also helps to improve the crystallinity, facilitate the homogeneity of nanoparticles, as well as to reduce the accumulation rate. And the objective of my project is, firstly, to synthesize the single-phase NSMO perovskite via thermal treatment method, and to study the effect of varying PP concentration on the structure and microstructure, electrical and magnetic transport properties of NSMO sample. And now let's move on to the literature review part. So in this paper, Yap et al. Has successfully synthesized the LSMO using thermal treatment method. And in their study, they find out that by increasing the calcination temperature from 500 to 1000 degrees Celsius, the crystalline size and particle size is getting larger, while the magnetic properties is also affected as well. And next, in this paper, Ahmad et al. Prepared the hard and soft ferrite by using one pot technique. And from their result, they discovered that the grain size distribution is more homogeneous when 0.02, 0.03, and 0.04 gram per ml of PP is used compared to other concentration. Besides, they also find out that the magnetic behavior will change as the PP concentration increase. And now let's move to the methodology part. And I have divided my methodology into two parts, which is sample preparation and sample characterization. And the table show the mass required for each particular weak percentage of PP concentration used respectively. So firstly, for the sample preparation, the precursor powder will be mixed with distilled water according to the stoichiometry ratio. And then the solution will be undergo stirring process for 30 minutes to make sure that they are well mixed. And next, the PEP will be added into the solution by using burette and continue to be stirred at 80 degrees Celsius for 2 hours. And next, the sample will be poured into Petri dish and drying in the oven at 130 degrees Celsius for 24 hours. The sample was then put into the crucible and undergo calcination at 500 degrees Celsius for 5 hours. And next, the powder will be grinded using pestle and mortar for 30 minutes and press into pellet form before undergo the sintering process at 1000 degrees Celsius for 10 hours. And next, for my sample characterization, the structural behavior will be determined using FTIR, Fourier transform, infra spectroscopy, and SRD, X-ray diffraction, and also the FISM, field emission scanning electron microscope. And for my electrical and magnetic transport properties will be identified using Hall effect measurement system. And now let's move more detail to the result and discussion part. So from the FTIR analysis, the dominant peak of pure PEP were found at 2,937, 1,644, 1,423, and 1,278 of wave number, and each of them are assigned to different type of bonding motion. And by comparing all my sample with the pure PEP, the result confirm that the non-existence of PEP in the sample, as there is no associated peak of my sample have been detected with the dominant peak of the pure PEP. And next, after indexing the SRD pattern, all NSMO samples show orthorhombic structure with PNMA space group. However, pure NSMO phase can only be found when 20 and 50 of PP is used, while the presence of Nd0.7Sr0.3MnO3 as the secondary phase are detected for other concentration. Besides, the percentage of secondary phases for 10%, 30%, and 40% are 5 and 9 respectively. In addition, the crystalline size is also generally increased after we do the calculation using Scherl equation. And the result is in line with PSEM analysis where the average particle size obtained for 20% and 50% are 179 nanometer and 186 nanometer respectively. And now let's go to the electrical property part. The resistivity value for pure NSMO, which is 20 and 50%, is at around 22 and 24 ohm cm and is slightly higher compared to other concentration where the value is from 2 to 7 ohm cm. In addition, we find out that the TMI is shift to higher temperature as the PVP concentration increase, as the crystalline size of the NSMO is increased when the PVP concentration increase. And then by doing the low temperature fitting, we are using our raw data to fit it with the theoretical model, which is with the formula here, which is rho t equal to rho naught plus rho 2 t squared plus rho 4.5 t power of 4.5, and each of them represent different interaction respectively, where rho naught is the residual resistivity due to grain boundaries, rho 2 is the electron scattering, while the rho 4.5 is the combination of electron menon, and electron phonon scattering. And by comparing all of the rho naught, rho 2, and rho 4.5 values, we find out that the resistivity in our sample at low temperature region is mostly contributed by the grain boundary effect, as the value that obtained for rho naught is highest among all. And next, we are fitted our result at higher temperature region with SPH, which is small polaron hopping model. And by using formula rho t equal to rho naught t exponential EP, which is the activation energy, over the Kb, the Boltzmann constant, and also the T. And after we plot the fitting curve and we substitute into the formula, we find out that the activation energy for 20 and 50 is much higher compared to other concentration. It means that the electron will be having difficulties to be hooked, and thus the resistivity for 20% and 50% is higher compared to other concentration. And next, for another region, the model is then fitted using VRH, which is variable range hopping model, by using formula rho t equal to rho naught exponential t naught over t. And by finding the slope, we can determine the value of t naught, which is the characteristic temperature that can be helped to calculate the density of state of the material. And lastly, for the magnetar transport properties, this is the magnetar resistivity behavior. This is a typical magnetar resistivity graph that we will be obtained for manganite sample. And it is clearly shown that the graph is divided into two parts, which is from 0 to, which is the gradient is more stable at the lower magnetic field compared to the higher magnetic field. And it means that the intrinsic magnetar resistance effect is more dominant, especially at low temperature, as we can see in the black line. For all of the 10, 20, 30, 40, and 50% of PP use. And lastly, in this graph, both graphs are showing the same trend where the temperature is, when the temperature is lower than 200, it means that the extrinsic MR is more dominant for 20 and 50%, while for temperature higher than 200, which is from 200 to 300. The intrinsic MR is more dominant for 20 and 40%, and it is mainly because of the contribution of the secondary phase that we are discussed before in the SRD analysis. So in conclusion, the removal of PVP from all samples was confirmed through FTIR analysis, and from SRD analysis, the pure NSMO phase is produced when 20 and 50% is used only, and the crystalline size and particle size is generally getting larger from both SRD and PSEM analysis, and the resistivity for pure NSMO phase is much higher. The activation energy for pure NSMO phase is slightly higher and harder to hold. And lastly, the intrinsic MR is mainly contributed by the formation of secondary phase. And in one word, we can say that in this project, the concentration of PVP does not affect much on the properties of the sample, while the contribution of the secondary phase have played a more important role to control the structure and microstructure as well as the transport behavior of my sample. And this is the Gantt chart for my study. And this is the reference that I used to prepare this presentation slide. And here's come to the end of my presentation, and thank you for your attention.
Okay, thank you, Hon Xiao Tong, and let's move to the Q&A. So, from your peers, questions, please.
Hi, Hon.
Hi.
Okay, hi, I'm Zarina. Just would like to know regarding the sample preparation. You choose for the 5 hours heating. Can I know why you choose for the 5-hour heating? Any significant of selecting of the 5 hours?
You mean for the calcination?
Yeah.
Because before we start before I start my study, we in our lab we already start to do some preliminary experiment, like based on the experience that my lab mate they find out there for thermal treatment and Sojau method, the suitable temperature for calcination is around 500 degrees Celsius for 5 hours. It's the most optimum one for the calcination process.
So that's why you choose for the 5 hour, right?
Yeah.
Okay. Okay, thank you.
Okay, thank you for your question.
Okay, any more questions? There's plenty of time here.
Yeah, I have one, Prof. This is Chan.
Okay.
I know I have two, actually.
Okay.
Okay,
First
go ahead.
is on your magnetoresistance slide, you show 5 graph. The next one.
Yeah.
There's 80, 100, 120, 140. What are those things?
This is the temperature for the material. We for the Hall effect measurement, we will undergo the characterization from 80 degrees Celsius until 300, which is the room temperature, because we want to find out that where is the TMI that our sample will go. So as I explained earlier, we can see there is 2 gradient, right, for the graph. And as you can see in the third graph, which is around 20%, you can see that this region there are straight line, right? The gradient is showing the straight line.
Okay.
So it means if we obtain the gradient is in straight line instead of we getting the gradient divided into 2 parts, it will mean that in this sample the intrinsic MR is more dominant at the certain temperature. And it means that the temperature that show the straight line will be near to our TMI, also the TC.
Okay, thank you. Another question. Yeah,
Okay.
This is more to a silly question, but I think it's quite, I'm not sure how it works.
Okay.
Because from your 5 slides before this, maybe 5 or 4 slides before this,
You mean the result and discussion?
Result discussion part, when you show a lot of numbers part. This one, SRD part. you show like the RP, the percent one, just below the crystalline size. You show 1, 2, 3, 4, 5, 6, 6 significant figure. I'm not sure how it works. Do we need to show that much? Or
You mean this one?
yeah,
The RP? Actually, this one is from the program which is that we use to analyze the chi-square plus to calculate the chi-square value, and the chi-square value is represent the goodness of fitting, where we can know that whether our raw data from the sample is matched well with the database in the SRD or not. So actually, I just take from the program.
Yeah. I just want to clarify, because I myself, I don't know the question, the answer also. Do we need so many decimal place to like
I understand.
very sure
The
about
significant figure, right?
what is the significant where is the significant reason to have more than four decimal place?
Actually, I think it depends on the preference, because for me, I want to get a more accurate result. That's why I take more significant figure.
Yeah, you take 1, 2, 3, 4, 5, 6.
Yeah.
Because these lines you have 6. Another one you have 3 to 4, something like that. Because your significant value keep on changing. I'm not sure how it works, because me, I'm not sure how many significant values should be during our presentation of that task.
Okay, I understand, and I will improve on this. And thank you for your suggestion.
Yeah, I'm not sure also.
Okay.
That's
Thank
it.
you.
Thank you.
Okay. Any more questions? We still have a lot. Couple more minutes. Nobody. Please do note that with your questions, there will be more marks involved. So you need to ask more questions to help your other fellow candidates to better present your seminar presentation later on. Maybe your your supervisor or co-supervisor. These are not quite my area, so I will not be able to ask the intelligent questions. So I guess if there are no questions, we could finish off earlier. I give one last chance. Dr. Lim, you want to say something?
Doctor, we cannot.
Maybe I answered just now the Chan question. Actually,
Okay, right.
Can you hear me?
Yeah.
Can you hear me?
Yes, doctor.
Yeah, we can hear you.
Just to answer, can you hear me? Okay, just to answer just now Dr. Chan question. Actually, most of the time we didn't put so much decimal point in our result, because even though that is the simulated value, but normally we didn't put. In the paper, normally we put only three decimal point or 4 significant figure around that. Yeah, the one that Hon you put inside there is too much already. Okay, because even because some of the paper they do put a lot, because they assume that that is a simulated value. Okay, so they want to show the how accurate is it their result. That's why they put a lot of figure inside. Yeah, just to answer back the
Chan.
Dr. Chan.
Doctor, he is not doctor yet. He's still studying PhD.
His name might be similar to Dr. Chan, but it's not Chan.
Oh, just to answer Chan. Okay. Normally we didn't put so much what call it going to be soon. So yeah, we didn't put so many figure inside there. Okay, normally it's about 4 you do it.
So
Okay.
maybe since Dr. Lim is here, so what is the normal practice for simulated data thing? Dr. Lim?
It depends. I seen before in many different journal. It depends on the reviewer as well. Some will accept the significant figure up to 4 and 5 because this is a simulated value, so you can have the decimal point up to 9 or 10 or whatever, a lot inside there. But some will comment, ask you to reduce to 3 significant figure. Some let you put until 4 or 5.
Okay.
Yeah, normally there is no rules and regulations strictly how many. Yes.
All right. Okay. So that clarifies a little bit more. Okay. I think we reached to the end, but if there are any more questions, I'll let you ask one more. Otherwise, I will stop now. I will stop the recording, and then please stay back until I've taken your attendance. Okay. So I will stop the recording now.